I'm pleased to have Marco bring us home for this year's version of Gauge Theory Virtual. After Marco's talk, we'll probably take a break and start back again in the fall. So Marco, it's all yours.
Thanks very much for the invitation, Dave. So today I'm going to talk about a work with Cipriano Manolescu and Lisa Piccirillo about relative genus bounds in indefinite form manifolds. I know that some people here in the seminar have already seen some version of it, so I'm sorry that there would be some repetitions, actually a lot of repetitions. So I think I want to start by giving you the big picture of what I'm planning to do. And the big picture is a big picture. So this is a big picture of a four manifold. It will be denoted by X. This is a closed four manifold. And the first thing that I want to do is to remove a four ball so that it becomes X minus the interior of a four ball. It's still a compact manifold with boundary S3, and I will denote it by X circle. I will use this notation for the rest of the talk. So whenever there is a letter for a four manifold with a circle on top of it, it denotes that four manifold minus the interior of a four ball. And then let's consider a knot K in the boundary of the fourth manifold, which is S3. Then I want to study all possible possible surfaces that can be embedded in X circle. And the question that we want to answer is the question of the minimal genus. So given a closed smooth fourth manifold X and a knot in the boundary, and fixed some homology class alpha, the question is, what is the minimum genus of a surface sigma smoothly and properly embedded in X circle, such that the boundary of sigma is the knot K, and sigma lives in the homology class that we fixed at the beginning. So technically, sigma defines a homology class in the second relative homology of X circle relative to its boundary, but this is canonically isomorphic to the second homology of X. So this is the question. Maybe I want to highlight one word, which is smooth. I'm going to focus on smooth embeddings, but of course one could ask the same question for locally flat embeddings, and I will say a couple of words about that. Okay, and some motivations for these questions come from some special cases that one could think about. For example, if you choose K to be the unknot, that is the easiest possible knot, then the question is about finding surfaces with boundary the unknot. But you can always cap off X circle with a four ball, and in that four ball you can always cap off sigma with a disk. So what you get is a closed surface in a closed four manifold, and you're asking what is the minimal genus of a closed surface in this closed four manifold in some fixed homology class. And this is a relatively classical question. This is called the minimum genus problem, which asks exactly the question that I've asked. And I want to say that gauge theory has proved particularly suited to tackle this question. For example, a landmark result is by Kronheimer and Mrowka. I think it was published in 1994, and that's the proof of the Thom conjecture, which establishes the minimum genus problem for CP2. And it says that every surface smoothly embedded in CP2 has genus that is greater than or equal to the genus of an algebraic surface. That formula d minus 1 times d minus 2 over 2 is the by the genus degree formula is the degree is the genus of an algebraic surface. So you could restate the Thom conjecture by saying that algebraic curves in CP2 are genus minimizing in their homology class. And there is a generalization of this result by Oshvat and Szabo, who proved the symplectic Thom conjecture. So they proved an analog of the conjecture for symplectic surfaces in closed symplectic four-manifolds. Okay, then the second special case of the question, so let's go back to the main question. The main question is, let's consider a surface embedded in a four-manifold with boundary S3, and let's try to find the minimum genus in its homology class, given that the boundary is a prescribed knot. So we tried to ask, we tried the special case when K is the easiest possible knot, the unknot. Now let's try the case when X is the easiest possible for manifold, and that's S4. So when you remove a 4 ball, what you get is B4. So what you're really looking for here is, given a knot K in S3, what is the minimum genus of a surface with boundary depth knot? And that's also another classical question. That's the question of the slice genus. We say that the slice genus of a knot K, denoted by G4 of K, is the minimum genus of all smoothly embedded surfaces in B4 with boundary given knot K. And the question that I mentioned earlier just reduces to determining the four-dimensional slice genus. Sorry, the slice genus of the knot K. A special case is when the knot admits a smoothly embedded disk delta in the fourth ball with boundary that particular knot. And in such a case, we say that the knot is slice, or in this talk, classically slice, because we will introduce other notions of sliceness. And delta is called the slice disk, a slice disk for K. Given a knot K, there are in general more than one slice disk, even up to isotopy. Here is some notation. Throughout the talk, I will use the letter sigma to denote a surface, usually with boundary, and delta will be reserved for the cases when the surface must be a disk. So this notion of sliceness actually generalizes to other four manifolds, and this is really this is really connected to the question that we were asking at the beginning, because we're looking for minimum genus surfaces inside some four manifolds. So let me give a couple of definitions. The first one is that a knot in S3 is slice in a fourth manifold X, where X is a closed fourth manifold, if it is the boundary of a disk that is smoothly embedded in X minus the interior of a fourth ball. So, a surface, so a knot is classically slice if it is a slice in S4. So this would sound like the standard, the most natural generalization of sliceness to other four manifolds. But there's another one that actually has already appeared in literature and in a joint paper with Manolescu, Sacker, and Willis. We decided to go for the name H-slice, just to try and distinguish the two notions of generalization. So knot is called H slice in X if it bounds a smoothly embedded disk in X circle, and moreover, the homology class of the disk is vanishing in H2 of X. So it's a null homologous slice disk. And as I mentioned, both of these notions are generalizations of classical sliceness, because a knot is classically sliced if and only if it is sliced in S4, if and only if it is H sliced in S4. The homology condition doesn't mean anything in S4 because S4 has trivial second homology. So next, I would like to give some motivation for why you would like to care about sliceness in the context of four manifolds. And the main motivation lies in the smooth Poincare conjecture in dimension 4. Given a four-dimensional smooth manifold, a four-dimensional smooth manifold X closed, the smooth Poincare conjecture in dimension 4 says, in one of its equivalent forms, says that that if that fourth manifold is homeomorphic to S4, then it is actually diffeomorphic to S4. And people don't seem to know whether it's true or not. I think that maybe 10 years ago, I had the feeling that most people in the field would have bet on the smooth Poincare conjecture in dimension 4 to be false. And now I see more people that maybe would bet on it being true. So I really don't know if it's true or not. Well, if I knew, I guess I would win a Fields medal. But here is a proposed strategy to disprove it that was outlined in a paper of Friedman, Gomb, Morrison, and Walker. The idea is the following. If you can find a knot K that is sliced in some four-manifold X homeomorphic to S4, but is not classically sliced, so it's not sliced in S4, well, then that means that the two manifolds X and S4 cannot be diffeomorphic to each other. Otherwise, either the knot would be sliced in both or not sliced in both. And if such a manifold exists, it is called an exotic four sphere. So again, for the moment, we do not know if exotic four spheres exist. But more generally, one could try to adapt this strategy to show that there exist exotic pairs. So by exotic pair, I mean a pair of smooth closed four manifolds, X and X prime, that are homeomorphic to each other, but not diffeomorphic to each other. And it is known that these actually exist. This is a famous result of Donaldson, for which he won the Fields medal. And the question that we would like to tackle is whether the Friedman-Gomb Morrison-Walker strategy can say anything, at least for exotic pairs that are not homotopy for spheres. And we do not know for sliceness, but we know that if we use H sliceness, then the answer is yes. And this is one of the main results of our paper. So the theorem is that there exists an exotic pair, X prime, and a knot K in S3, such that the knot is H slice in X prime, but not in X. So the set of H slice knots can detect that the smooth structures on X and on X prime are different. And the easiest working example, so, by minimal, I mean somehow the easiest to find here. It's not the minimal. I mean, we don't know if it's the minimal under some definition of minimal, like be too small, but presumably not. So the smallest working example we could find is where x and x prime are the K3 surface blown up once and the connected sum of 3 CP2s and 20 CP2 bars, and K is the right-handed trefoil. And I want to mention here a couple of remarks. There's a recent paper of Ida, Mukherjee, and Taniguchi, where they gave infinitely many examples, infinitely many. So this was implicit in their paper. I don't think they wrote it explicitly, but they find infinitely many knots that are H-slice in x prime, but not in x, using the same x and x prime. And that infinite family consists of knots that lie in different concordance classes. So it's a pretty generic one. And maybe I want to mention that the theorem was already known if you consider knots inside some 3 manifold different from S3, and if you consider 4 manifolds x and x prime that are not closed, and for which the boundary is that 3 manifold y. So for instance, here one could take Akbulut corks. If you have a quark is a contractible 4 manifold that admits an involution on the boundary. So by using quarks, one can prove this result. Okay, so this was some motivation for sliceness. Now let me give you some examples for sliceness in 4 manifolds. So let me set up some notation. S of x is the set of knots that are sliced in x. So just the usual set of sliced knots, but in any 4 manifold x. And S lower h of x is the set of knots that are h sliced in x. And K is the set of all knots. Then we have some inclusions. If you take the set of knots that are sliced in S4, these are the classically sliced knots, then they are always contained in the set of H-sliced knots for any 4 manifold X, simply because you can choose the slice disk to lie in the neighborhood of the boundary. Then if you have a null homologous slice disk, you certainly have a slice disk, so you have the second inclusion. And finally, the set of slice knots is, of course, a subset of the set of all knots. And all of these 3 inclusions can actually be equalities, but there's something. So the set of all knots and the set of H-slice knots in X are always different. And this is a result of Klug and Ruppik. They actually proved it for topologically H-slice knots. So they showed that given any closed 4 manifold X, you can always find a topologically a knot that is not topologically H-slice in X. And so in particular, it is not smoothly H-slice either. But now let's see some examples for some 4 manifolds. So the first example is S4. For S4, you have that 2 equalities are true just by definition. And the last one is not true. If you want, this is also a consequence of Klug-Ruppik, but in this case, it's just the existence of a knot that isn't slice. And there are some 4 manifold that behave exactly like S4. For instance, S1 cross S3, which can, so this is a case where you can go back to the case of S4 just by doing surgery on an S1 fiber, and and in that case, the set of slice nodes and H slice nodes doesn't change. And another interesting case is T4, because the universal cover of it is R4, and the set of H slice nodes again doesn't change if you go to sorry, not doesn't change. So if you yeah, it doesn't change if you go to the universal cover. Then another interesting case that somehow is at the opposite end of the spectrum is S2 cross S2, where the first two inclusions are proper and the last one is an equality. And some examples here are the zero-framed weighted doubles of non-sliced nodes are always not sorry, zero-framed weighted doubles of let's say a knot with tau greater yeah, with tau non-zero are always non-slice. So you have to choose the positive weighted double of, say, a knot with tau greater than 0. This was a result of Manolescu-Owens. But you can prove that such a knot is always H-slice in S2 cross S2. Then, in order to find a knot that is not H-slice in S2 cross S2, you can use an abstraction coming from the Arf invariant. And the equality at the end was proved by Suzuki. It's actually a pretty simple proof. You could explain it in a class on knot theory. Then the next example is CP2, which is a definite manifold. In this case, all the inclusions are proper, and here are some examples. So the right-handed trefoil, the left-handed trefoil, and some torus knot give you a knot that is in one set, but not the previous one. And the last example that I want to mention is the K3 surface. So for the K3 surface, I will use a picture from the Gompf-Stipschitz book about Kirby calculus. So this is a handle diagram for K3. And for the K3 surface, the first two inclusions are proper, and here are some notes that prove it. And interestingly, the last one is unknown. We thought about it for some time and we couldn't really solve it. So the question is whether every knot is sliced in K3 or not. And we have no idea. Oh. And maybe before we move on to the next section, I want to say that from the handle diagram of K3, one can see that there is a complicated handle that is in a trefoil shape. And that complicated handle actually gives you a slice disk for the left-handed trefoil in K3, with the property that its homology class is non-zero because it winds over a handle exactly once, but it the intersection form computed on it so delta squared is actually 0, and this comes from the fact that the handle is zero-framed. So now I would like to move to some literature review, and then I will explain the new theorems that we prove. So if you look in the literature, the families, so all the various results about giving lower bounds for surfaces with boundaries certain not in a given homology class can be categorized in two main families. The first one is given by topological bounds. And topological bounds, by topological bounds, I mean bounds that also work for topologically flat surfaces in topological fourth manifolds. So these results are not particularly helpful if your goal is to distinguish between smooth structures. So I'm going to quickly review them, but keeping in mind that our goal is different. So the first invariant that obstructs, that gives you obstructions is the arc invariant. So a general theorem that is obtained by combining Rockley's first theorem with some work of Friedman and Kirby is the following. If you have a characteristic surface sigma, a characteristic class sigma, then the arc invariant of K plus the relative arc invariant of X sigma plus the signature of X minus sigma squared over 8 plus the Kirby-Sieberman invariant of X is an even number. And now I don't want to explain everything here, but the relative arc invariant of X sigma is 0 if sigma is a disk, and the Kirby-Sieberman invariant is 0 if X admits a smooth structure. So for, say, a particular case of a spin for of a smooth spin for manifold X, and if a knot is H slice in X, then the arc invariant must be 0. And for instance, this gives you an obstruction to H sliceness for S2 cross S2 or the K3 surface. Another topological bound comes from the Levin-Tristram signatures. And we have two main results here. One is from Rocklin and then generalized by Viro and Gilmer, which says that by studying the Levin-Tristram signatures, they basically study signatures of Trenchit covers of X over sigma, and they find that the signature of K plus the signature of X is lies in a certain interval, essentially. There is also another theorem by Conway and Nagel that looks very similar to the previous one from a formal viewpoint, except that it works for some other values for some other signatures, for some other values of omega on S1. And Conway and Nagel only proved it for null homologous surfaces. So they're rather complicated, but let's see what they say, for instance, for K3. If you apply either of the previous ones for the K3 surface and for the standard knot signature, so that's the Tristram-Levin signature with omega equal to -1, then you find that if a knot is H slice in the K3 surface, its signature is between -6 and 38, which is a nice interval. So you know that somehow this has to be bounded. All right, so this was for the first family of invariants that I put in the category topological bounds. Now there's another category that comes from studying negative definite fourth manifolds. When you have a negative definite fourth manifold, then there are then you can unleash the power of gauge theory, basically, and so you have several results. So one is from Oshbat and Sabo. You get that the L1 norm of the class of sigma plus sigma squared is bounded by 2g of sigma minus 2 tau of k. And here tau is an invariant from Hegar's homology. There is also an instanton analog of that by Kronheimer and Rovka. There is an extra technical condition. If your surface can be homotoped to the boundary of your four-dimensional surface, then you have the same inequality as before. So note here that if a surface can be homotoped to the boundary, then the homology class is 0, and so the left-hand side of the inequality is always 0. And S sharp plays the role of 2 tau here. And then I also want to mention a result of myself with Manolescu, Sarkar, and Willis, where we prove the same using not gauge theory, but Kovanov homology. But it's not for every negative definite four manifold, but for connected sums of CP2 bar, and also for sigma null homologous. However, note that it's not known whether there exists negative definite and simply connected closed four manifolds that are not connected sums of CP2 bar. So in principle, we just proved it for all negative definite simply connected four manifolds. Maybe not. Okay, so now I want to move to the new results. So I want to note here that we saw previous results we set the previous results in two categories, one given by topological bounds and the other by the category of negative definite four manifolds. So now we want to study smooth bounds, bounds for smooth embeddings inside indefinite four manifolds. And there is some literature here as well. The main result is actually the first technique, the main technique that we use, that is the adjunction inequality. So if you have a pair X S where X is a smooth closed four manifold and S is a spin-C structure on X, then you can define the Seiberg-Witten invariant of XS and the Auerbach-Szabo invariant. Actually, maybe here I want to add some condition, let's say P2 plus of X greater than 1, for instance. There are some results that go under the name adjunction inequality that are due to several people. If B2 plus of X is greater than 1, X is of simple type, which is a technical condition on the Seiberg-Witten invariant of the Auerbach-Szabo invariant, and sigma is a closed, smooth, embedded surface in X with positive genus, then if either of these invariant, the Seiberg-Witten invariant or the Auerbach-Szabo invariant is non-zero, then you have an inequality that is somehow is analogous to the ones that we mentioned earlier for negative definite four manifolds. So you have the first Chern class of S, which is a two cohomology class paired against the class of sigma plus sigma squared less than or equal to 2g of sigma minus 2. The word that I want to stress in this theorem is that sigma is a closed surface in X, and basically what we want to do is to find some kind of relative version of that, because we want to study surfaces with boundary a given knot. So here is the strategy that we follow. We start with our fourth manifold X minus the interior of a fourth pole. We have a knot K, and we're supposed to have some surface sigma with boundary K, and we want to give bounds on its genus. Then we try to cap off the fourth manifold with a four-dimensional piece that I call Z, and we also cap off the surface sigma with some surface F sitting inside Z. So now, after we glue them, what we get is a a closed surface in a closed four manifold, or maybe just a four manifold in some cases. And so we can apply the previous adjunction inequality. So this is somehow the first main strategy. So the easiest case you can try is to set Z to be a fourth ball, which is the easiest possible fourth manifold. And then for F, you can choose a genus minimizing surface for the mirror of K, the mirror because you're gluing from the opposite direction, inside the fourth ball. And so the result that you get in this case, so assuming that X has some non-vanishing Seider-Witten invariant or Schwarz-Sabo invariant, then you get an adjunction inequality with an extra term at the end given by twice the genus, the fourth genus of K. Okay, that's already something, but we can do better. So it is actually better if you try to cap off X with a two handle. So you can attach a two handle along K, because in such a case, F can always be chosen to be a disk. So in case one, rather than choosing the four manifold as simple as possible, we choose the surface as simple as possible, we choose a disk. And the easiest way to do that is to attach a two handle. So you may note that if you glue a two handle to some four manifold with boundary, what you get is not a closed four manifold. But nonetheless, we can still apply the adjunction inequality. We just checked that we can apply, we proved, we checked that version of the adjunction inequality still, this version of the adjunction inequality still works for manifolds with boundary. And so we get the following result under the assumption that the Seider-Witten invariant, the Schwarz-Sabo invariant of XS is non-zero. Then we get an adjunction inequality completely analogous to the previous one, except that now we get twice nu plus of K bar, where nu plus is an invariant coming from Hierarch-Floer homology. And it's basically the optimal choice of a framing coefficient for the two handle that you're attaching. So if you make this optimal choice, then the Schwarz-Sabo invariant of the fourth manifold with the two-dimensional handle attached is still non-zero, and so you can still apply the adjunction inequality. And we know that we get something better than before because nu plus of K bar is always less than or equal to the fourth genus of K. So here is some comparison. If you choose X to be the K3 surface and S the spin structure on K3, with it's actually the canonical structure. So C1 of S is 0, and you check, well, it is proved that the Schwarz-Sabo invariant is non-zero. This is a result of Schwarz and Sabo. And theorem 0 says that if the boundary of sigma is the right-handed trefoil and sigma squared is positive, then the genus of sigma is positive. But theorem 1 says that in such a case, the genus of sigma has to be greater than 1. So, so you need at least genus 2. So you get some strengthening. One thing that theorem 1 doesn't tell you about is H-sliceness. Because if a knot is H-slice, then sigma, the homology class of, sorry, if you want to consider if you want bounds on surfaces that are null homologous, then the left-hand side of the equality is 0, and the right-hand side is always non-negative, because nu plus is greater than or equal to 0, and g of sigma is positive by the assumption, by the hypothesis of the adjunction inequality. So for h-sliceness, you need a better idea, but somehow we can deal with it using the same idea of gluing some four-manifold and some surface inside it. So in this case, we choose Z to be a symplectic four-manifold minus a four-ball. And the theorem that we get is the following. Suppose that X and W are closed symplectic four-manifolds with B2 plus congruent to 3 mod 4. This ensures that the Auschwitz subinvariants are non-zero. Then if you know that the mirror of K, that I denote by K bar, bounds a disk in W circle with in homology class that is non-zero but that squares to 0, then K cannot be H-slice in the other four-manifold X. So I feel that it's easier to give a picture of it rather than explaining it. So here is a picture and at the same time a proof, an idea of the proof at least. So we consider a four-manifold X, a knot sitting in the boundary which is S3. And let's suppose by contradiction that the knot K is H-slice in X circle. And let's derive a contradiction. Okay, by hypothesis, we know that K bar bounds some disk delta in W circle. So you can glue the two disks together. And now the condition that delta squared is 0 and delta is in non-zero homology class tells you that you have a zero-framed sphere inside the closed four-manifold X connected sum W. And moreover, this I didn't write, the homology class of this sphere is non-zero. Then a result of Intuition and Stern says that this is impossible if, oh, here I forgot a hypothesis. No, I didn't. So this is impossible if the Seiberg-Litten invariant of the four-manifold is non-zero. But now the problem is that this four-manifold is a connected sum of two four-manifolds with positive with B2 plus greater than 1. And there's a vanishing result that tells you that that the Seiberg-Litten invariant will always be vanishing. So that's too bad. But we can actually solve the problem by using Bauer-Furutas invariants. So the Bauer-Furuta invariants are a refinement of the Seiberg-Litten invariants. And so they are some stable co-homotopy class, stable map between spheres coming from taking finite approximations of the Seiberg-Litten maps. And nicely, they do not necessarily vanish for connected sums. And there are some examples where, oh, whoops, sorry. And there are some nice examples where they don't. So one such example is when X and W are closed symplectic four-manifolds with B2 plus congruent to 3 mod 4. In such a case, you can compute what the Bauer-Furuta invariant is, and you can compute that the Bauer-Furuta invariant for the connected sum is non-vanishing. So let's see an application of this theorem. I mentioned that this theorem can actually give an obstruction to H-sliceness. So one first result is that the right-handed trefoil is not an H-slice knot in K3 or even K3 blown up once. And the proof is just by applying theorem 2. So we need to recall that the left-handed trefoil bounds some disk that is not null homologous, and such that its homology class satisfies delta squared equal to 0. This was because of the handle picture of K3. Then you can apply theorem 2 with W equal to K3 and X equal to K3 connected to some CP2 bar, and you get precisely that the right-handed trefoil is not H-slice here. A corollary of the corollary is that we have a knot K, the right-handed trefoil, that is not H-slice in this manifold X, that is K3 blown up once, but it is H-slice in another 4 manifold, 20 CP2 bar connected some 3 CP2s, that happens to be homeomorphic to X. The fact that the 2 manifolds are homeomorphic is a consequence of Friedmann's theorem, and so you actually have an exotic pair that is distinguished by the set of H-slice knots. So you may ask why is the right-handed trefoil H-slice in X prime, and the reason is that it is actually already H-slice in 1 copy of CP2. So this is a nice exercise if you want to think about orientations. Yeah, maybe I should warn you that the speaker has failed this exercise several times and got that the left-handed trefoil was H-slice in CP2, but that's not true. And finally, a corollary of the corollary of the corollary is that the right-handed trefoil is a topologically H-slice knot in X, but it is not smoothly so. The fact that it is not smoothly so is just stated in the corollary, but now we know that X and X prime are homeomorphic, and so the right-handed trefoil is H-slice in X prime, and so it is also topologically H-slice in X prime, because a smooth disk is also topologically flat disk. And being topologically H-slice is a property that is preserved under homeomorphism. All right. I have still 10 minutes, am I right? Okay.
Yes.
Okay, thanks. So in the last minutes, I'd like to give an outline of another technique to detect to obstruct H-sliceness. It still uses gauge theory. So in particular, it uses Furutas Theorem. And let me recall it first. So Furutas theorem says that if X is spin, closed, and indefinite, then its second Betti number is bounded below by 10/8 of the signature of X plus 2. And there is a very nice paper of Donald and Wafai where they used this result to obstruct classical sliceness, so sliceness in the 4 sphere. But really their proof can be quickly adapted to work in any spin for manifold. So what we get is that if K is an H-slice knot in a spin for manifold, and if W is a spin 2 handle body with boundary the 0 surgery on K, then if the sum of the 2 Betti numbers is not 1, 3, and 23, which is a technical condition that I will explain in a second, then we have an inequality involving the Betti numbers of XW and their signatures. And well, what's happening here? I think I have missed something. Oh, there we go. So here is the idea. The idea is that you consider the exterior of an H-slice disk. You call it V, and then you can apply Furutas theorem to negative V union W, which happens to be spin, because the crucial point here is that every spin structure on the zero surgery of K extends to V. So when you glue V and W, you're sure that you still get a spin for manifold. And then you apply Furutas theorem, but really you apply a refinement of Furutas theorem by Hopkins, Lin, Shi, and Chu. And this is why you get the funny-looking condition of the sum of the Betti numbers being different from 1, 3, and 23. And let me show you an application. Here's a note that I call KDV for Donald and Wafai. The figure is actually taken from their paper. And they showed using their abstraction that this knot is not sliced in S4. And then they proved that it is topologically sliced in S4, and presumably, if I remember right, by computing the Alexander polynomial. What we can prove is that, in fact, this knot KDV is not H-slice even in K3. So we found another example of a topologically sliced knot that is not H-slice in K3. And maybe here I want to spend a couple of words because we had another example of a topologically sliced knot in a fourth manifold that is not H-slice in that fourth manifold. But somehow the two knots are qualitatively different, because in the case of KDV, we see that the dichotomy between the topological category and the smooth category actually comes from S4, because KDV is already topologically sliced in S4, but not sliced in S4. But for the other knot that we found, the right-handed trefoil, the right-handed trefoil is neither topologically sliced nor smoothly sliced in S4. So when we showed that it is topologically sliced in one fourth manifold, but not in a homeomorphic fourth manifold, then we actually said something interesting about the smooth structures on that fourth manifold. So I guess that's more or less the end. I have listed some open questions. The first one is something that I've already mentioned. We do not have any example of a knot that is not sliced in K3. And we actually don't know whether they should exist or not. So on one hand, K3 is an indefinite fourth manifold. And for the two examples of indefinite fourth manifolds that we have, namely S2 cross S2 and CP2 connected sum CP2 bar, every knot is sliced. But on the other hand, K3 is spin and symplectic, so that should pose some strong restrictions. So we don't know what to expect here. But maybe I can tell you that we prove that every knot with a knotting number less than or equal to 2 is sliced in K3, and Mukherjee actually strengthened our proof to show that every knot with a knotting number at most 4 is sliced in K3. So if you find a knot that is not sliced in K3, then it must be very complicated. And the second question is whether sliceness can detect exotic pairs. So in our work, we showed that H-sliceness detects exotic pairs. But we have not been able to show that sliceness detects any exotic pairs, even for indefinite Fork manifolds. So this question stands. And then before introducing the last question, I want to, yes, I'll just recall this theorem of Klug and Ruppig, where they showed that every smooth closed Fork manifold has some knot that is not topologically H-slice. And this implies that every smooth closed Fork manifold also has a knot that is not smoothly H-slice, because smoothly H-slice knots are also topologically H-slice. But one could ask a question about this inclusion. Is this proper or not? And we found some examples where this is proper, actually including, if you want, even S4 is such an example. But we didn't find any example where this inclusion is not proper, so the inclusion is inequality. So we asked this question: given a smooth closed Fork manifold, is there always a knot K that is topologically but not smoothly H-slice in X? And I think that I'd like to conclude here.
Okay, I think we can thank Marco. Are there questions for him?
Hi, Marco. Thanks for the great talk.
Hi, Ali.
I'll ask a question. So, is there any hope of? I guess you know the pair of exotic pairs that you guys have. We already know that they are exotic for some other reasons. Is there any hope that your techniques can be used to find some new exotic pairs?
It's not likely. It's not likely because the techniques that we are using are really techniques that show you that the two Fork manifolds you start with are not smooth, are not diffeomorphic to each other. So somehow we're implicitly using that fact to show that the knots, so that the set of H-slice knots can distinguish them. So it's kind of working backwards.
I see.